Hello. This chapter is about nuclear chemistry. Nuclear chemistry is different from other chapters because other chapters we study the reaction of compounds, and chemical reactions always happen at the valence shell electrons, right? They have kind of exchange of electrons, pairing up and breaking bonds, things like that. But nuclear chemistry, the things happen inside the nucleus. So first of all, we have to understand what is inside the nucleus. And yeah, you know from your high school that normally in nucleus they are composed of two major things. No? So first is the proton, and secondly there is neutron. Proton is positively charged, neutron is neutral. And not only proton and neutron, we have like electrons that orbit around the nucleus, like this. So the electron here is positive, is negative, right? The charge is negative. So if you look at this kind of structure, you can see that positive charge of the proton has electrostatic repulsion or repulsive force in the nucleus, and make the nucleus itself is not really stable, right, because of the electrostatic repulsion. But we know that we have several hundred types of atoms, several hundred types of nucleus. All of the nucleus composed of proton, and you have electrostatic repulsion, except hydrogen atom, because you have only one proton, right? But since helium with two protons, so you have electrostatic repulsion. Or if you go further higher order into like uranium with 92 protons. So 92 protons have very huge electrostatic repulsion in the nucleus. So it's not very stable. That means they have something to be stabilized here in the nucleus. Make your protons can stay there together, right? So there are so many mechanisms to incorporate it to like facilitate the nucleus to be like that. First of all, it's quite similar to electron. As you know, electron has spin, right? Proton as well, creating a spin. So if proton creating a spin, every charged particle moving in circular motion or spinning like this, it created the magnetic field. Right? It's a magnetic field. So proton with magnetic field, somehow this one have to pair up together to reduce the magnetic moment. Similar way with the electrons. But we don't really know exactly what happened in the nucleus because we cannot, like, it's unlike electrons. When we think about electrons, we can just eliminate electron, kick it out from the atom, and we can then study the shells of electrons, things like that. But we cannot do that for the nucleus. But we're quite sure that that somehow neutron and proton can like pair up and making stabilized energy by the magnetic moment, thing like that as well. One thing is proton, okay, can transform to be neutron. Proton is a charged particle, 1 plus, right? So this is the atomic number, right? Normally atomic number indicate the positive charge in the nucleus, right, for any other elements. So we use that style of writing up the nuclear symbol for proton and neutron as well. So down here is the positive charge, right? And the mass number of proton is 1. It can transform to be neutron, right? This is in nuclear physics. You have to learn nuclear physics in high school somehow, no? So if proton transform to be neutron, it have to release something in order to conserve the mass and charge. So the mass is already conserved. So another particle that is emitted from this kind of exchange or transformation have to use the mass number as 0. But anyway, the charge have to be conserved as well. So it have to create something positive with mass number equal to 0. And this thing is called meson, M-E-S-O-N. Excuse me. Okay. Meson thing here is quite not only produced from this transformation. The meson produced in this transformation can recombination with the neutron and turn the equilibrium back to proton like this. So as you can see, proton can transform into neutron, and also neutron, which is 0, 1, can transform to be proton like this, but in exchange it have to give you a negative charge of the meson here. So meson negative has the nucleus symbol similar to electron, right? Negative charge, 1 minus, and the mass number is equal to 0. The things of the meson differ from electron is this mass. Even though the mass number is 0, that means it's closer to 0 AMU, but actually it has some kind of masses. But the mass of meson is higher than the mass of electrons, about 100 something times greater. So it's not the electron itself, it's something else which more massive comparing with the electron. We can also identify it by putting positive and negative meson here. So in this, we can say that if we have proton and neutron, so by this kind of transformation, it's like proton and neutron can swap the place. Because proton can transform to be neutron, neutron can be transformed to be proton. So number of proton, number of neutron is quite crucial for the stability of the nucleus. The way electron and neutron pair up or arrange the magnetic moment of themselves is also very important. But we don't know exactly, as I said, how they pack together, you know. One of the things that I want to show is if you look at the mass of proton, it is equal to 1.6726 times 10 to minus 27 kilogram, and mass of the neutron is equal to this 6749 times 10 to minus 27 kilogram. This is the exact mass of proton and neutron. So in order to create a nucleus of carbon-12, carbon-12 is the nucleus is composed of 6 of proton and 6 of neutron. So the mass number is 12, right? So carbon-12 weighted how much? Because carbon-12 composed of 6 proton and 6 neutron, right? So if I give you 6 proton multiplied here, 6 neutron multiplied here, you can then use your calculator to find the mass of 6 proton and 6 neutron, which is dropped to, let I use my calculator. It is 1.6726 plus 1.6749, and then multiply the whole things with 6. It would be 20.09 approximately, 20.09 or 85 actually, times 10 to minus 27 kilogram, right? So this is the mass of 6 proton and 6 neutron. But the mass of carbon-12 exactly is 19.92 times 10 to minus 27 kilogram. What you can see here is the mass of proton and neutron incorporated into constructing carbon-12 is not equal to the mass of carbon-12 itself. And more importantly, the starting material is heavier than the final product. So that means you have some mass loss by this kind of things. It seems like impossible, because it's like when you put 6 apples and 6 bananas together in a basket. But now the mass of the fruits in the basket is less than the mass of apples and banana, right? So why? Why? So as you can see, there are some kind of mass lost, right? So mass loss over here is called delta M or mass defect. And the mass defect here is equal to something, right? but the mass defect, mass loss here is transformed from the mass itself into energy. There are energy and mass transformation, right? Using this kind of very famous equation, E equal to mc squared. But m here is delta M, is the mass defect. Multiply with c squared, you have the energy here. And the energy here is called binding energy. Binding energy. What is the binding energy? This is the energy to bind all proton and neutron together in the nucleus. And this is a very huge amount of energy. So it has to be at least overwhelm the electrostatic repulsion of the proton, of the positive charge in the nucleus. So this is very huge. If you don't believe that, you just multiply with c squared, right? The speed of light is 3 times 10 to 9, right? Oh, no, 10 to 8, right? So c squared is 10 to 16, right? 10 to 16. And then you compete with 10 to minus 27. So that's drop down to minus about 11 or 10, right? Joules. That's for just one atom, right? So if you think about 1 mole of carbon atom, right? 1 mole of carbon, you have to multiply this kind of thing up with the Avogadro's number. So you can see that the amount of energy required to fix all proton and neutron together in carbon 12 like this is so huge. It's so huge. And this is why we're trying to take this kind of energy out, okay, and use it for some kind of applications. This is how importance of the nuclear chemistry. And this means that one of the mechanisms to lock the nucleus to be like this, proton and neutron all together, you need that kind of binding energy, which is called nuclear force, right? Make this happen. And also because of the interchangeable of proton and neutron. So that means you reduce down the charge density. Instead of positive charge being here, it can swap the place. So that means you like move the positive charge from one place to another. So it's like resonance effect, thing like that. Right? So reduce down the electrostatic force. I would say the electrostatic potential energy here in the nucleus. And because of the pairing up of proton and neutron. So number of proton and neutron is also important for the stability of nucleus. For example, if we know that the number of elements in the world today, actually the element in the world is number 1 to number about 92 uranium. But bigger than that, we have to synthesis, right? We have to do some kind of reactions to synthesize all these kind of heavy elements, okay? And for the data gathered until today, we have 118 types of element. Starting from one proton to 118 proton in the nucleus. But not every nucleus is stable. And one element may have more than one isotopes. For example, we know that like proton, right, hydrogen atom, you have first isotope, 1 proton and 0 neutron, because you have only 1 proton, no? So there's not necessary to have neutron to stabilize the nucleus, right? So proton is one of that. Then we also have another isotope. The proton sit with the nucleus, with the neutron in the nucleus. So in the nucleus, not only proton, you have neutron as well. This is second isotope of hydrogen. And another very famous isotope of hydrogen is called tritium, right? 1 proton and 2 neutron. So one element may contain more than one type of isotopes, right? So 118 elements, you have about 1,000 isotopes, right? Many hundreds isotopes, right? But on those many hundreds isotopes or 1,000 isotopes available in the nature, there's just some of the isotope that is very stable. Proton can stay together in the nucleus. But some of the isotope is not stable because, as I say, the electrostatic repulsion force in the nucleus is very strong. And then your nucleus is ready to be decomposed out by some kind of energy thing like that, some kind of mechanisms. So in all 100 elements, there is only 281 isotopes that is stable. So isotopes of element can be divided into stable isotope and the thing called radioactive isotopes, because these are the unstable isotopes. So the isotopes or the nucleus of these isotopes decomposes and then produce radiation, alpha, beta, gamma, thing like that from your high school. So now, if we look at just a stable isotope, okay, number of stable isotope. Because, as I say, that it depends on this. It depends on the transformation between proton and neutron, and we believe that there are some pairing things between magnetic field of proton and neutron transformation here and everything. So number of stable isotopes may depends on the number of proton and neutron. So what we can see is if we have number of proton and number of neutron here, the isotope with even number of proton and even number of neutron, there are about 167 stable isotopes that compose of even number of proton and the even number of neutron, and about 57 stable isotopes that contains even number of neutron of proton but odd number of neutron. And then we have another 52 isotopes that have odd number of proton and even number of electron. And very, very rare that we have just only 5 isotopes that have odd number of both proton and neutron. So as you can see, odd even number is very important. So this is a clue that there are some kind of pairing up between proton and neutron, right? Examples of these are so many. Like for even number of proton and neutron, it's like carbon 12 is a stable isotope, right? You have even number of proton, even number of neutron, 6 and 6, okay? And carbon 13 is a stable isotope as well. Carbon has 3 major isotopes, 12, 13, and 14. Carbon 13 is stable, carbon 12 is stable, carbon 14 is not stable. So this is a stable isotope composed of 6 proton and 7 neutrons. So the number of neutrons is in odd number. What else? It's like, let's think about the potassium. Okay, potassium number 19 and the mass number is 39. As you can see, we have odd number of proton 19 but even number of neutron 20. And this is the major isotope found in nature, most abundant isotope, and very stable isotope as well. The example of this, just 5 isotopes, like nitrogen, right? N714, with 7 proton and 7 neutron. This isotope is stable, right? This is the most abundant isotope of nitrogen. And also for odd and odd number, like deuterium, H12, right? You have 1 proton and 1 neutron, it's also stable. But we have only 5 isotopes available for these categories. So as you can see, there are stabilities of isotopes. Now, if I want to plot a graph of stable isotope into the graph that show the relationships between proton and neutron, we can have some very important information to show. Okay, let's see the graph. Now if we put every single isotopes found in nature here into the graph, on the x-axis is the number of protons or the atomic number Z, right? And on y-axis is the number of neutron, right? I use the n instead of number of neutron. So we have n and Z. And if you look at this line is the line indicating n equal to Z. Or we can say that the neutron to proton ratio is equal to 1. Okay? It's equal to 1. And then we put every single isotopes inside. For example, if we have like carbon, right? Carbon contains 6 proton and 6 neutron. So I put it here. This is carbon 12. But we have other isotopes of carbon. Carbon 13, carbon 14, things like that. Put it here. Okay. From this graph, what you can see is there is a very narrow black line over here. Okay. Black line here. So the very narrow black line indicates only the stable isotopes. So the stable isotope on the black line here is called belt. The black line is called belt of stability. Okay. So the black line, I will like label it for you like this. So as you can see, the alignment of the line here at the very beginning for the very small particles, very small element, the black line is on top of the NP equal to 1. So that means the stable isotope of the small element almost always contain neutron and proton in equal amounts. But then after your elements growing bigger, you have more proton in your nucleus. You need higher number of neutron. So the ratio of N to P is increasing from 1 to 1 ratio to 1 to 1.1, 1.2 to 1.3. And then above here is about 1.4, 1.3, 1.4, 1.5, around that. So this is the belt of stability, which indicating that with a higher number of proton, you need even higher number of neutron. And the ratio is increasing from 1 to 1 to be higher, to 1 to about 1 to 5, 1 to 4, right? That is because if you have only one proton, there is no repulsive force. You don't have to use neutron inside. But if you have 2 protons, you have intermolecular, you have charged particle here is the repulsive force between 2 protons. But if you have 3 protons, right, instead of having one pair of repulsion, you have the 3rd proton over here. So you have like 3 pairs of repulsive force. And if you add one more nucleus, one more proton over here, it adds up to be 6 pair of repulsion. So it's like the electrostatic repulsion among proton is increasing a bit kind of exponentially up, right? So you need more of neutron when you have higher number of proton. I mean the ratio is increasing as well. Okay, so this is the belt of stability. So if your element is not in the belt of stability, you have to like try to push them push them back to the belt of stability. Okay. One thing that I have to show you here is, as you know, that the element contains proton, no? And yeah, if you look at the belt of stability is limited here at number 82. So this point is number 82, or this is delayed, right? And then from 83 and so on, bit mass is number 83, right? Bigger than that, there is no stable isotopes available. That means every isotopes of bit mass and the things that bigger than that can be decomposed very easy. This is because, as you know, if you have higher number of protons, then the repulsive force in the nucleus is stronger and stronger. So you need more neutron. And more than that, you need more binding energy that I've talked about already, right? You need more of the binding energy. So sometimes if the proton is so much higher than 83, that means there's nothing can hold your nucleus together. So it 100% decomposes. Okay, so the stable isotope can be found up to 82. More than that, proton is too much and nothing can survive. Okay, in nature, the biggest thing can be found is about 92, 93, about uranium, neptunium, around that. There's the highest number of proton found in the nature. Higher than that, we cannot find. So we have to synthesize things like that. And if it is less than 82, anyway, if it's less than 82 but it's not on the belt of stability, so it may be because you have less number of neutrons. So the repulsive force of proton is so strong and you have not enough neutron to stabilize the system. So your nucleus is not stable. This is N over P is less than belt of stability. So it have to be decomposes, right? And the decompose of this kind of element will eliminate the beta plus as a product, as a byproduct. This is the radiation. But if the neutron is too much, as you can see that there are interchangeable properties of neutron and proton. So neutron, too many neutron is also not very good. So if you have too many neutron, you have to get rid of those kind of neutron. So it decomposes with the blue color or give away the beta minus as the major product, as the radiation. So there are many reasons behind radiation. Can be divided into this color for beta plus, this color for beta minus, and if your element is very, very heavy, higher than 82, majority is yellow color, right? The yellow color is alpha particles or alpha radiation. There are actually articles of radiation as well, but we will not focus on these rare types of radiation. We will focus on alpha, beta minus, beta plus, that I will show you later from this slide. Okay, so now I just show you the belt of stability, and if it's not stable, it's not on the belt, it will trying to go back to the belt. Now we're going to look at how we can move things back to the belt of stability by some kind of radioactivity. Okay. So from the belt of stability that I've already shown you, so there's just some limited amount of isotopes that is stable and stay on the belt of stability. The belt of stability is ended at number 82. So if you have any kind of element that has higher number of proton more than 82, there's nothing stable. They have to decompose and then go back down to the belt of stability, force the proton to be less than 82 to make it stable because electrostatic repulsion of the positive charge in the nucleus. But not only that, if there is in the area of 0 to 82, but it's not on the belt, maybe above the belt or maybe under or below the belt, you have to move it back to the belt. So the mechanisms to put everything back to the belt, there are three kinds of radioactive radiation here. First one is called the alpha radiation. Alpha radiation or alpha particle is actually the nucleus of helium. Right? That means your nucleus release the nucleus of helium out or release two proton and two neutron all together at once. Okay? And we call this kind of radiation as alpha radiation. The second alternative is the beta plus or positron. Right? The beta plus here, beta plus radiation, is actually the particle of the thing called antiparticle of electron. You know the electron, right? Antiparticle of the electron is the particle with the same mass of electron, but with opposite charge. So electron is negative, so positron is positive. So if the nucleus is unstable somehow and release the beta plus, that means your nucleus release the positron. Another kind of radiation is beta minus, the beta radiation but with the negative charge. This is actually the particle of electron. Oops, I put it in the wrong way. So 0 is the mass number of electron. So I shall put it here. Okay. So there are 3 types of radioactivity that I want you to fill in here. But before that, beta plus, beta minus, or positron and electrons is released from this kind of transformation. Proton transform to neutron, a neutron can transform to proton. During this kind of transformation, it can release these 2 particles. Okay? Proton to neutron, release 1 particle. Neutron transform to be proton, release another kind of particle. Which one belong to which direction, forward or backward? You have to guess and then put it back here. So the reason of the radiation of these 3 kind of things is in here. If proton is higher than 83, what shall happen? If your nucleus is above the belt, what kind of radiation shall happen? And if your nucleus is below the belt, what kind of radioactivity can be found in this kind of thing? And I also give you some examples. The first example is the polonium 210. Polonium 210 is belong to this class because of proton is too much, right? So you have to reduce the number of proton somehow. So what kind of radiation can be happen, and can you fill up the equation over here? And then carbon 14. Do you know that the stable isotope of carbon is carbon 12 and carbon 13? So if this is not stable, it must not stable because of some reason, right? And how can you do it? Okay? And how can you stabilize it? By which kind of radiation? And the last question is this 2 element, cobalt, isotope 58. The stable isotope of cobalt is 59. And the stable isotope of iridium is 192. This is 191, so this is not stable. But how this can stabilize the things, right? So you have to release something, alpha, beta, alpha or beta plus or beta minus, and why. Okay, so think about it and trying to fill this equation up. Okay, that's your assignment. So see you again in the next clip for the answer of this assignment.